and then 3 minutes in between for questions. My name is Jonathan Balkind. I'm an assistant professor in UC Santa Barbara. I do have one talk in this session, so you'll see me ask some very insightful question on that one. Our first talk here is from Gus Smith at the University of Washington. Gus is a sixth-year PhD student in the Pulse Lab there. He works at the intersection of programming languages and hardware design, as you can see from the talk that he'll be giving. And he is currently looking for industrial research jobs. I strongly encourage you, having worked with Gus, I can say he'd be a great colleague. Gus, please go ahead and tell us about FPGA technology mapping using sketch-guided program synthesis.
Great. Thanks so much, John. So yeah, like John said, my name is Gus Smith. I'm from the University of Washington. I'm from the Pulse Lab, University of Washington. And today I'm going to be presenting our work on improving FPGA technology mapping, which we so lovingly call Lake Road. And like John said, I'm looking for a job. If you need somebody who can do compilers, hardware design, and PL stuff, please reach out to me. This talk represents more than 2 years of work from a very big team of people. It's not just me, obviously. And many of them are in the room today. So if you see them, please say hi. And with that, let's jump into the actual content. So FPGAs are a popular reconfigurable hardware platform. They are composed of small hardware primitives. For example, lookup tables that implement logic functions, registers which hold state, and DSPs which accelerate specialized computations like arithmetic, among many other features. A key step in the process of compiling an input design down to an FPGA is called technology mapping, and it involves choosing a subset of the primitives such that they implement the input design. To produce an optimal compiled design, it's crucial that we efficiently utilize the primitives on the FPGA, taking full advantage of specialized units like DSPs to produce a design which is smaller, faster, and more power efficient. However, we have found that during our research, when mapping designs, state-of-the-art technology mappers often do not efficiently use primitives, especially programmable primitives like DSPs. So for example, imagine that this design here could be mapped to a single DSP if the DSP was configured in the correct way. The state-of-the-art technology mapper from Xilinx, however, might fail to discover a mapping to the DSP using additional LUTs and registers, leading to a larger, slower design. In response to this discovery, we built a technology mapper that we call Lake Road. Lake Road is powered by our core insight. Configuring programmable primitives like DSPs is like writing programs, so use a tool called program synthesis. And if you don't know what program synthesis is, don't worry. I'll give a brief primer later in the talk. Applying program synthesis to technology mapping produces a technology mapper which is more complete than existing tools. That is, it finds more mapping opportunities and produces smaller designs, while also providing stronger formal correctness guarantees and being more extensible than existing tools. So this brings us to the overview of the talk. The problem that we're addressing is that existing tools fail to utilize programmable primitives. Our insight is that when mapping to programmable primitives, you should apply program synthesis. And we use this insight to build Lake Road, which is more complete, more correct, and more extensible than existing technology mappers. This also gives us our roadmap for the talk. So we're going to first describe the problem and the insight in more detail. Then we'll talk a bit about the implementation. And lastly, we'll talk about Lake Road's evaluation of its completeness, and we'll briefly discuss correctness and extensibility. So let's begin with the problem. We claim that state-of-the-art tools fail to use primitives efficiently. So let's dig into exactly what this means with a real-world concrete example. Let's imagine a hardware designer is trying to compile this design, which simply computes an add, followed by a multiply, followed by a bitwise AND, onto a Xilinx UltraScale Plus FPGA. The Xilinx UltraScale Plus FPGA architecture, like most FPGA architectures, contains plenty of LUTs and registers. But for maximum performance, our hardware designer is specifically aiming to use the architecture's specialized DSP primitives. They know that if programmed correctly, the UltraScale Plus's DSP, which is called the DSP48E2, can efficiently implement their design. That is, if the DSP is programmed to select the adder, the multiplier, and the AND unit, it will implement their add, multiply, AND module. Thus, we'd expect that we should be able to compile this entire design using just a single DSP on the FPGA. But when we actually go to do this, when we actually attempt mapping with Xilinx's proprietary state-of-the-art compiler, which we can't actually name due to licensing reasons, we find something odd. The compiler produces a design which does in fact use a DSP, but also uses extra LUTs and registers, which are completely unnecessary. And if you think this sounds like a toy example, it only takes a little Googling to find developers online experiencing the exact same mapping failures. So the state-of-the-art tool has failed us. Now what? Do we just give up and accept suboptimal results? Well, at this point, if we don't want to give up, there's really only one other option, which is to actually manually instantiate the DSP. And by manually instantiate, I mean our designer is going to have to handwrite the Verilog, which instantiates the DSP. And to make it super concrete, here's an example of the Verilog that they're going to have to write. And you don't really need to understand Verilog to see how unpleasant this would be to write by hand. Each of these lines represents a separate port or parameter of the DSP, which they must determine how to set by reading through Xilinx's manual for the DSP48E2, which if you haven't read through it is 75 pages long. And the manual describes the complex interdependent constraints between the dozens of ports and parameters, which makes determining a valid DSP configuration really painful. Even once our designer has gone through that painful process and written implementation by hand that uses a single DSP, they still have no formal guarantees that their implementation is actually correct. They can attempt to catch bugs via testing, but they have no way of knowing that they didn't miss an edge case of the DSP that's buried somewhere deep in the manual. So to recap where we are, state-of-the-art tools failed to produce an efficient mapping. It cost our designer a lot of time and effort to do it manually. And in the end, they don't even know if their output is correct. But let's step back a bit. So to configure the DSP, our hardware designer had to write all of this code by hand. To do so, they had to consult extensive documentation, which documents the combinations of ports and parameter values that are legal and which ones are not. Given all of this, it's fair to say that the experience of configuring a DSP is a lot like writing a program in a domain-specific language that's embedded within Verilog itself. So this realization brings us to our core insight, which is that configuring DSPs and other complex primitives is very similar to writing a program. So use a technique from the field of programming languages called program synthesis. But what actually is program synthesis and how does it work? So we'll now move on to from describing our problem and insight and turn our focus to the implementation of Lake Road and specifically how it utilizes program synthesis. So at a high level, Lake Road is a tool which takes an input design and uses program synthesis to produce a low-level implementation. So let's see how program synthesis is actually used within Lake Road. Internally, Lake Road is actually using a specific type of synthesis, which is called sketch-guided program synthesis. Sketch-guided program synthesis begins with a sketch, which captures what we want our compiled output to look like, in this case, a DSP48E2. Crucially, sketches have holes, which will be filled in automatically by a constraint solver. In our example, Lake Road begins with a DSP48E2 instantiation, where crucially the values of the ports and parameters are holes that are going to be filled in by the solver. We then generate a constraint for the constraint solver, asserting that this sketch is equal to the design that we're compiling, in our case, the add, multiply, and. We then query a constraint solver like Z3 to determine whether there's any way to fill in the holes to make this assertion true. If there is such a solution, the solver will return that solution to us, which we'll then use to fill in the holes in the original sketch, producing a compiled design that can be returned to the user. And because we generated this implementation with a constraint solver, it comes with a strong correctness guarantee. That is, if you trust the constraint solver, you can actually trust the compiled output because you know this constraint is satisfied. Lake Road relies heavily on the Rosette language for its implementation of program synthesis. So while we don't have time to dive any deeper into implementation, I will tease at one of our technical contributions. And in my opinion, this is one of the most interesting tricks of the paper. So if you've tuned out of the talk at this point, you should tune back in just for a bit so you can listen to this part. So one thing to note is that the solver doesn't actually know what this expression means. That is, constraint solvers like C3 don't understand Verilog code. So how do we actually make the solver understand what this Verilog means? Well, luckily, Xilinx releases models of all of their primitives. Ostensibly, these are for simulation. And these massive Verilog files encode the exact functional behavior of the primitive. Lake Road introduces a technique that we call semantics extraction, which utilizes the open source hardware synthesis tool Yosis to convert vendor-provided simulation models into semantics that are comprehensible to the underlying solver like Z3. Semantics extraction has potential applications far beyond FPGA compilation, which is why I'm so excited about it. And to learn more about it, please read the paper. So with that, we're going to quickly move on to presenting our evaluation. We're going to primarily focus on Lake Road's completeness. So specifically by completeness, what we mean is that Lakeroad finds more mappings than other tools. Going back to our original add, multiply, and example, remember that the state-of-the-art tool from Xilinx maps the design using extra logic units and registers, while Lakeroad successfully maps the design using just a single DSP. To evaluate our completeness claim, we're simply going to expand on this example. First, by adding additional tools like Yosys, and second, by adding more benchmarks, by enumerating a large set of designs, all of which should fit onto a single DSP according to the DSP's documentation. So we go through the documentation, we enumerate these designs, and for Xilinx, we end up with over 1,300 benchmarks in total, all of which should go onto a single DSP. We then run each of these 1,300 benchmarks through each compiler, and we collect the results. And we're going to now plot those results. So let's begin with Yosys. Yosys successfully maps about 2% of the 1,300 benchmarks to a single DSP, represented by this small green bar. On the rest of the benchmarks, Yosys fails to find a mapping to a single DSP using extra resources like LUTs and registers. The state-of-the-art tool from Xilinx does a lot better, mapping over 30% of designs to a single DSP. However, Lakeroad outdoes them both, mapping twice the number of designs to a single DSP. And these same results hold across the other two FPGA architectures we evaluate on, which is Lattice ECP5 and Intel Cyclone 10 LP. So with that, we have demonstrated completeness by showing how Lakeroad finds more mappings than other tools. I'm going to very quickly now go through correctness and extensibility, just very, very quickly. So our correctness claim is that Lakeroad provides stronger correctness guarantees than other tools, which is very easy because the other tools we compare against provide no correctness guarantees. Lakeroad, on the other hand, provides a strong guarantee of correctness due to its use of solvers. And if you'd like to learn more about this, please see the formalization section of our paper. Lakeroad's extensibility claim is that it more easily supports new FPGAs. Again, please see the paper for details where we show how via semantics extraction from Verilog and other technical insights, we were able to add support for a very wide variety of FPGA primitives across 4 different FPGA architectures. With that, we finished our discussion of Lakeroad's evaluation. Before we conclude, I want to very briefly touch on a future direction for Lakeroad, which is primarily scaling up to larger designs. I know a lot of people might have this question. Lakeroad is meant to be used as a subroutine invoked directly on submodules that you want mapped to DSPs and other specialized units. We're currently developing methods that will automatically find places in a design where you can invoke the Lakeroad subroutine. So if you want to hear more about that, please come talk to me or ask a question about it. And finally, Lakeroad is open source on GitHub. We just actually did a release of binaries for Mac OS and Linux. It comes pre-built with examples that they should just be able to run out of the box. And allow me to conclude with a summary of the talk. We have shown how existing tools fail to utilize programmable primitives. We have delivered the insight that when compiling to programmable primitives, we should use program synthesis. We use this insight to build Lakeroad, which is more complete, more correct, and more extensible than existing tools. Thanks, everybody, and I hope you'll go use it.
Great talk, Gus. This is Olivia from Stanford University. I had a question about why for Lakeroad on the Xilinx Ultra scale, you guys weren't able to reach near 100%, whereas for the other hardware, you guys were.
Yeah, so I had to smooth this out for the talk. It makes it kind of weird to put red at the top of the Xilinx bar. So if you want to read the paper, you can see more details. That block that we don't map is actually a mix of unsat for people who do solver stuff. This means that Lakeroad tells us those benchmarks can't actually go onto a DSP. Super interesting. We have a discussion in the paper. It could be that the simulation model is wrong for the DSP. It could be something on our side. We haven't fully dug into these. It's interesting, and you should read the discussion in the paper. That black portion is just timeout, and solvers timeout. Program synthesis times out. That's a thing we deal with. That's just a fact of life.
That was going to be my other question, which is absolute time. How long does it take the solver on average to run?
Let's take a look. Here's some plots. So it's on the order of tens of seconds generally. It's actually pretty widely different per architecture, depending on the complexity of the symbolic executor that's symbolically executing the extracted Verilog. But if you look compared to the other compilers, they're kind of all over the place. Vivado, which, yes, I just said it by name, takes a long time. We take somewhere kind of in the middle. Yosys and Diamond Yosys and Diamond are pretty fast. So it's a big range for these compilers.
John Demme, Microsoft. What makes FPGA tech mapping so different from ASIC tech mapping?
That's a really good question. You know, I, not being an FPGA person, despite just giving this talk, I actually don't know super well. We are doing a little work on mapping to standard cell libraries now. So ask me in 2 years and I will tell you. I think part of it is that FPGAs have things like DSPs that are basically like programmable little CPUs. You know, I don't think you really have that as much in the ASIC world.
Yeah, far more complex than standard cells.
Yes, yeah.
Thank you.
Thank you.
Thank you very much, Gus. And we can give him another round of applause. So the next talk we'll have here is TAPA CS, as is by Neha Prakriya here, who's a third-year student at UCLA in her PhD. She's working with Jason Kong on scalable accelerator design for efficient AI. And today's work will be on enabling multi-FPGA designs today. So Neha, please take it away.
Thank you. So as John just mentioned, I'm Neha. I'm doing my PhD with Professor Jason Kong, and today I'm presenting our framework called TAPA CS, which enables scalable accelerator design on distributed HBM FPGAs. The main motivation behind our work is to easily scale up from a single FPGA to multiple FPGAs. We propose a framework which takes as input any large user design and partitions and maps it across the cluster of FPGAs, such that the user now has access to virtually unlimited accelerator fabric, high bandwidth, memory, and capacity. There are some challenges in exposing such a framework to the user. And such frameworks have existed for GPUs for very long, like where you can specify that I want to use 3 GPUs and the model will be spread out across the 3 GPUs in a model parallel or data parallel fashion. But with FPGAs, there are a couple of challenges that we need to address. The first is the varying cost of communication across the memory or storage hierarchy. For example, the on-chip communication cost is much smaller than off-chip to the HBM or off-chip to another FPGA versus internode between 2 different FPGA clusters. So there's a need to partition and map application code while taking into account compute load balancing between the FPGAs, the network topology in which they're connected, and the resource utilization of the user application. Finally, we want to ensure high design frequency. So TAPA CS augments the traditional CAD tool flow of Vitis HLS to introduce floor planning steps and pipelining steps within scheduling and binding phases, where we expose to the tool the devices that are available in the cluster, as well as the internal chip layout of the FPGA. So modern FPGA boards consist of multiple chiplets or dies, and crossing the boundary of multiple dies is expensive and causes routing failures and frequency degradations. So we expose this structure of the FPGA to the tool very early on so that you can floor plan in an intelligent manner. Modern FPGAs also consist of several hardened IPs for performance reasons, like the platform IPs or the PCIe IPs, and routing around them is often challenging. So we also expose that information very early on. So we take as input the user code expressed in C++ data flow and create a compute module graph. This graph consists of several tasks communicating with each other through FIFOs. We extract these tasks and synthesize them in parallel before floor planning them across the multiple FPGAs that are available to you. I go deeper into this step in the next slide. Then we insert the communication logic between the FPGAs. For this, we're using an open source software by AMD called Alveolink. The cost of communicating is about 1 microsecond at best, and the bandwidth that you have available per port is about 100 GB per second. We then floor plan the design across the FPGA within the chiplets so that you have no routing congestion and you spread the design out. And finally, we introduce pipelining at all the die crossings to ensure high design frequency. So the inter-FPGA partitioning step is we use an ILP mapper to do that. Our objective here is to decide task to FPGA mapping. And we consider whether the FPGA you want to place this task on has enough resources or not based on what you've already placed there. And we also want to minimize the cost of communicating between that task that's now on, say, FPGA 1 with all its neighboring tasks that might be on different FPGAs or on different dies of the same FPGA. Here you consider the varying costs that we discussed earlier, the off-chip media that's used, whether it's Ethernet or PCIe, and the data transfer volume between the tasks. So the cost function looks something like this, where you consider the FIFO bit width between the two tasks, VI and VJ. You also consider the distance, which is the cost of communicating between the two FPGAs, and this depends on the topology information that the user provides. And finally, we also have a scaling factor to adjust the cost for different interconnection media, whether it's PCIe or Ethernet. So we evaluate TAPA-CS on a server equipped with 2 nodes, each of which feature 4 U55C boards. These are connected in a ring topology, but the topology can vary if that's the case in your server. And we use Alveolink, as I discussed earlier, which has a best case latency of 1 microsecond. To solve the ILP mapper that I discussed earlier, we use the Gurobi solver, which is free for academia. We evaluate across multiple different benchmarks, namely CNN, PageRank, KNN, and Stencil. We have 2 baselines. One is the single FPGA Vitis design, and the second baseline is the single FPGA TAPA design, which is basically a single FPGA design with the floor planning steps within the multiple dies. So we are using this to make sure that our performance gains are also due to spreading out across FPGAs and not just because of the intelligent floor planning and pipelining. And F2, F3, and F4 refer to the 2, 3, and 4 FPGA TAPA-CS designs. So first, let's look at the Stencil kernel. So Stencil kernels apply a sliding window of computation on any input array to produce an output array. Such a Stencil kernel can either be memory bound or compute bound, depending on the number of iterations. And the specific kernel that we pick is the Dilate kernel from the Rodinia HLS benchmark, which is a 2D 13-point Stencil kernel. We vary the iterations from 64 to 512. The single FPGA baseline with Vitis can route a design with 64 iterations, 15 PEs, and an HBM bit width of 128. Larger iterations and PEs fail on a single device due to routing congestion. As we increase the number of iterations, we measure the compute intensity in terms of the operations per byte of external memory access, and we find that the design becomes more compute intensive as the number of iterations increase. Smaller designs with 64 or 120 iterations are more memory bound. Also, the transfer between FPGAs increases in case of designs with more iterations. So to scale the design to better suit multiple FPGA execution, for the designs with 64 and 128 iterations, we increase the HBM channels that are used. And for the designs with 256 and 512 iterations, we increase the number of Ps. The 4 FPGA design for 64 iterations is about 5x faster than the single FPGA Vitis baseline. The 4 FPGA design for 512 iterations is 2.3x faster than the single FPGA baseline. The main reason for the decreasing improvement as the compute intensity increases is that the transfer volume for the design with 512 iterations is much larger than the design with 64 iterations, and you can no longer amortize that cost of communication when the compute gets divided between 4 FPGAs. That's another reason why there are lesser gains for the Stencil design compared to the next benchmark that we will discuss. And that's because the Stencil design is almost sequential, where the FPGAs cannot be launched in parallel. Until you finish executing your previous PEs, you cannot really launch the next few FPGAs. So let's take another example that's better suited for multiple FPGA execution, which is the PageRank algorithm. This accelerator implements the citation ranking algorithm, where you load an input graph from the host to the device HBM. Then you stream in edges from the HBM onto each PE, where you calculate and propagate the weighted rankings from the source to destination vertex. Then these updates are stored back in HBM and reloaded to accumulate the final rankings. The single FPGA baseline in this case can route 4 PEs using 27 HBM channels. To scale the design, we increase the PEs from 4 to 8 to 12 and 16. And in this case, the inter-FPGA transfer volume does not depend on the compute intensity, but depends on the input graph. So when we partition the design across 4 FPGAs, we find that the design is about 6x faster than the single FPGA baseline across all the graphs. So this is much better than the Stencil benchmark that we saw earlier. And we also have a frequency improvement because of the pipelining step that I introduced earlier. Sorry. And another important factor in this case was that unlike the stencil design, once the first FPGA that contains the vertex routing module completes execution, the rest of the FPGAs that might have a subset of the other modules can be launched in parallel. So it displays more parallelism just with the structure of the design. I don't go into details of all the benchmarks, but the 2, 3, and 4 FPGA designs are on average 2.1x, 3.2x, and 4.4x faster than the single FPGA baseline. We also have a frequency improvement of between 11 to 116% compared to Vitis HLS. We already have some successful demonstrations of using TAPA-CS. This work was with a team at UCSD, where they have used it for mass spectrometry clustering across multiple FPGAs, and it's published at DAC 24. We also presented it at the BioSys workshop on Saturday, if you were there for that one. So mass spectrometry is a very important topic in proteomics, which is a fundamental pillar in biological research. It's used to identify proteins in drug discovery and a lot of other important applications. But the problem is that these databases are often very large. The one at UCSD is now hundreds of terabytes and requires distributed acceleration. And clustering that's also been GPU accelerated before still takes a couple of days to run on these large databases. So our 4 FPGA design for this mass spectrometry clustering, which uses hyperdimensional computing to reduce the search space and embed the mass to charge ratios into a higher, more informational dimension, is about 2.7x faster than the single FPGA design. And it's about 11x faster than the previous state-of-the-art FPGA design and 17x faster than the state-of-the-art GPU design. So I'd be happy to take any questions, and I would love if you could check out our repository and use it. Thank you.
Any questions from the audience here while we wait? I wanted to kind of ask about, I'm really interested in the aspects of scaling up really far. And because you have to feed the topology in early, I'm wondering about situations where kind of what you might think about if you had relatively complex network topology between the FPGAs, but you use something more conservative when you did your design kind of optimization in the first place. Do you think that that would penalize you by a lot, or do you think that that would still work well if the design itself was kind of more constrained than the available networking?
So that's a good question, because we also thought about that, because most of our benchmarks so far have been kind of simplistic in that aspect. So now we are introducing in our next work some pragmas that the user can insert. If they know their application better, that they can say that we want to scale this aspect, but not scale this part of our application. So that's something that the user can control in future iterations of the work.
Thank you for that.
Thank you.
Any other questions here? Let me check the time. I wonder if you could say a little bit more about your mass spectrometer. This sounds really interesting too.
Sure. Do we have
we've got a minute, so you could say a little bit more. Yeah.
Okay. Yeah, so here we are using hyperdimensional computing, which Professor Diana Rosing at UCSD is an expert on. So we're embedding the mass to charge ratios of these different protein fragments into a higher dimensional space, and then we're clustering them. We also divide them into multiple buckets of small and large, and then that ensures that our distance calculation matrices are small enough to fit on chip. And when we spread to 4 FPGAs, you have so much more on-chip logic available that you can afford to store distance matrices, and you don't have to access HBM often. So that's something that we really benefited from here. Yeah, any other questions? I would be happy to take them.
We'll go on from Johnny. Go
ahead. Okay, John Deming, Microsoft. It was unclear. Did you test this technique on one FPGA, treating each SLR as a different FPGA?
No, we don't treat each SLR as a different FPGA, but we do consider the different SLRs and how we map across the SLRs to make sure that there's no congestion on one specific part of the board.
Yeah.
And also once we know the boundaries of different SLRs, we pipeline that boundary so that it's doesn't degrade frequency.
Did you compare that approach against not taking the SLR crossings into account?
Yes. So the F1V baselines that we showed don't take into account the, so this one does not take into account the crossings.
Yeah.
And does not pipeline it. This one does take into account the SLRs, but is still just one FPGA.
Okay.
So the one that does take into account the SLRs does perform better even for one FPGA.
Yeah. Great results. Thank you.
Thank you.
Okay. Our next talk here is from Thierry Wei from the University of California at Berkeley. He's a second-year PhD student advised by Krista Asanovich. He also works closely with myself and with Carl-Johan Seeger. Currently, he's working on microarchitecture and formal verification. And today you will hear about FPGA debugging in a really fast way.
Thank you, John. As a professor that I met a long time ago used to say, people who work in architecture inevitably end up working in verification. So today I'm here to present Zoomy, a software-like debugging tool for FPGAs. This is a joint work between Berkeley, University of California, Santa Barbara, and University of Washington, Seattle, or as I call it, Vivado Stockholm Syndrome Support Group. Why? So in this case, unlike prior work, unless the previous talks, we're trying to use FPGAs to validate ASIC. And let's say you have a design written in System Verilog and you want to make that into a chip. Should you do that immediately? Like some of the, less risky, more risky software practices where you can just push your code and fix it on the fly. And I think people usually don't do that because if you want to tape out, you really need a high confidence. So what you really do is you take that System Verilog, push it through Vivado or some other vendor tool, and you try to run it on an FPGA. And if everything passes on the FPGA and if all the software runs with good performance results, then you finally move on to ASIC and tape out and finalize the entire design. And that kind of leads to the cost of verification keeps growing, especially although what we do we call prototyping, although prototyping really takes the small chunks in this diagram. However, most of the bars below it also is predicated on the success of prototyping. So we really want to make prototyping as fast and as ergonomic as possible. However, that is not what people usually experience when they touch FPGA tools. And we call this a symptom, and collectively people experience the death spiral in FPGA prototyping. So what you really do is that, first of all, you start synthesizing your design. If you get lucky, 5 hours passed. If your design is really big, it can span into multi-days for really large FPGAs, which in software terms this is the compilation that, many people complain, oh wow, why does my linker take a minute to link? I must rewrite a new high-speed parallel linker that makes it take 5 seconds to link. Then you run your design into FPGA, and almost always you run into a crash in your software workload within 1 minute. By 1 minute, I'm just being generous to myself and many of the code example I see. This is because usually before you run it on FPGA, you run things in software simulation, and software simulation is anywhere from 1,000 to 100,000 times slower than FPGA prototyping. So for example, it takes several days to even put up Linux on an FPGA, but it takes mere seconds to do that. Oh, sorry, it takes days to put Linux in software simulation, but seconds on an FPGA. And what do you do after a crash? after a crash, you think really hard, you scratch your head. What are the signals that I need to see what's going on here? And after thinking really hard for 10 minutes, you add some signals and you realize that you need to restart the cycle from the start and you need to resynthesize the design all over again, enable to go forward and fix new bugs. And unfortunately, this is even the state of the art even in commercial tools. And so what are the problems here? So the problems here are manifolds. First of all, the lack of incremental compilation. And the debugging FPGA is more often than not post-mortem, which means that you are not debugging your problems at the point of crash. You are really debugging the problems maybe thousands or millions of cycles after the crash because your design on your FPGA is still running when you have that particular crash or you encounter that particular bug. And you don't really have any introspection visibility into the state of your FPGA to see what's really going on there. So that's why you need these really expensive recompilations over and over again to see what's going on. And even then, the stuff you can see is usually really small. It's like tens of signals for thousands of cycles. And this leads to inevitably this meme, which is, your manager, or in our case, your advisor asks, why are you running around in your office? And you told him your code is compiling. I just launched my runs on Vivado. And he's like, great, you can just do it, or you'll do whatever you want then. And PhD is not a good PhD is not judged by the number of years you do it. So you kind of don't want to spend the majority of your PhD years waiting for Vivado to finish its synthesis process. So that's why I want to speed it up. So that's why we take a look back in the software domain. The software domain has really mature answers over the years to solve these problems. For examples, you may have a GDB for actual introspection visibility, where you can see in real time the value of variables of statements, and you can control the stepping of the program. And in software, usually the incremental process is really mature. When you only change a single file, usually the recompilation that needs going on is very, very small. You don't really need to recompile things that you didn't affect. Unlike in hardware where even changing the connection of a wiring may gives you another pleasant few hours of recompilation. And you actually have a stack trace or some other mechanism for you to attach your debugger to a process so that you can actually debug a bug where it happens, not speculate where it might have happened and restart and wait for that crash all over again. So we call this in situ debugging. And so this is where we present Zoomy, a software-like debugger for Xilinx FPGAs. And so the boxes that's colored in green are the existing tool flow and the existing mechanism. And the boxes that are highlighted in blue are the ones that we introduce in this paper. So what the high level steps look like is that you have your user design, and it goes through some transformation by Zoomy. Then Zoomy also provides a vendor tool incrementalizer to help the vendor tool actually do proper incremental compilation. Then by both adding a very small IP to your design and providing a software interface for you to interface with your FPGA, you can actually gain a GDB-like debugging experience when you're doing FPGA development. So let's take closer looks at each steps of the death spiral to see how we're solving this problem. So our dynamic debugger, which is the GDB-like interface, provides these functionalities such as breakpoints, watch points, stepping, and until pause and replay, to FPGA debugging with support for off-the-shelf FPGA boards. And how do we do that? We want to introduce this new notion or new perspective in how we see FPGAs. And the traditional understanding that the FPGA is a bunch of homogeneous tiles that's connected in a mesh network. Each of these tiles have some reconfigurable synchronous or combinatorial elements that you can reconfigure to make them either perform some sort of arithmetic operation or to store some value. And you can kind of reconfigure how the things are connected together to perform different functions at a higher scale. However, we want to see that when we are studying the architecture of Xilinx FPGA in detail, we can see that actually that is, although that appears to be what's going on, what's really going on is that the so-called bitstream is just a binary executable. And really the core of the FPGA is a microcontroller running on the chip. And each tile of the reconfigurable logical elements is just like a normal MMIO peripheral, just like, things like just like another UART or simple things like that. And this is, however, this is for, over 10 years, 15 years ago when Xilinx still has good yields. And we now talk about how we adapt to 3D stacked FPGAs. So for 3D stacked FPGAs, you have different chiplets that connects together, and we may think about how the microcontroller and the control flow transfer looks like. And this, we discovered a hidden register in reverse engineering the bitstream. In that we noticed a bit pattern that appeared repetitively in a bitstream for a multi-SLR FPGA. And we discovered what that register is called in an open source TCL file, open source by Xilinx, as you do, of course. That's called bout. So how that works is that by having an empty write into this bout, you transfer the control flow between your different SLRs. And what is this? And we also reuse verification collateral, such as existing SVAs, into finite state machines that triggers and stops the whole design at the time of a crash, so that when you're debugging in situ rather than debugging post-mortem. And we support a wide array of features that's prevalent in open source tools, in open source projects. So lastly, we look at so in evaluation, we look at the compilation time in a really large, in a highly utilized LVO. And we can see that in subsequent improvements, we can achieve up to almost 20 times the speed up. And our assertion overhead has very little cost associated with it. And we selected random assertions prevalent in open source CPU cores, and we see that we can successfully transform all of them. And thank you. If you have any questions, feel free to ask you. And this is the GitHub URL where we're open source the code in short course.
Hi, my name is Kingshuk. So I ran into this issue that when you have a clock domain processing in the FPGA, sometimes if you have not configured it properly, it might cause bugs. So can this solution be used with designs that have multiple clock domains as well?
Yes, we have a discussion specifically in the paper on how we use this technique to properly deal with multi-clock designs. However, we do have a limitation that if you want to debug designs that have multiple clocks, you need to instantiate the debug controller inside the multiple domains, because because just by the very nature of async processing, you cannot trust the value sampled from another clock domain.
Makes sense.
Oh, hi. Thanks for the talk. Yeah, I'm Albert from Rutgers. So the question I have is, you mentioned you have watch points.
Mm-hmm.
So my question is, what are like the timing overheads for actually trying to use a watch point? So does the debugger like communicate on every cycle with the client interface, or is this all done on the FPGA internally? And what's the overhead of this like watch point mechanism?
So in the debugger, we have so in the actual hardware debugger that lives on the FPGA, where we instantiate as an IP, we have some hardware watch points where you can dynamically configure and use that to trigger, and that has little to none timing overhead. However, if you use up all of them, where you have to revert to normal software breakpoints, then it will have a lot of effect on timing overhead.
Okay, thanks.
Thank you.
I think that's all the questions we've got time for just now. Thank you, Thierry, very much. So next up, we have Kingshuk Majumdar. He completed his PhD from the Indian Institute of Science. His PhD thesis was on compilers for high-level synthesis, and he's joining Georgia Tech as a postdoc soon. His research interests include compilers, high-level synthesis, computer architecture, and programming language design. Please tell us about HIR.
Thank you. Hi, my name is Kingshuk, and today I'll be talking about our work, HIR and MLIR-based intermediate representation for hardware accelerator description. So we will talk briefly about the background and the motivation, and after that we'll talk about the HIR dialect and the compiler that we built around it. After that, we'll talk about the different parts of the compiler, such as the scheduling, optimization, and the backend, and finally we'll discuss the results. Okay, so first, let's briefly discuss what an FPGA is. An FPGA could be thought of as a 2D grid of hardware components, such as lookup tables, DSPs, and SRAMs, and that you can connect using a programmable interconnect to form arbitrary hardware circuits. Now, in hardware design, a very common abstraction is of FSMD. By that, it means that you have a data path and you have a finite state machine that controls the data path. The data path specifies what operations are performed and where to send the data, and the FSM specifies when to perform an operation. Okay, so now let's discuss the motivation of this work. We were encouraged by LLVM's success in the software ecosystem. What LLVM allowed is that new programming languages can target LLVM and benefit from all the existing optimizations. On the other side of the spectrum, if you're designing a new optimization pass, you could plug it into the LLVM compiler and the whole ecosystem could benefit from the optimization. This is enabled by LLVM's modularity and its intermediate representation, which acts as an exchange format between its passes. We wanted to replicate something similar for the high-level synthesis ecosystem. So now I'll talk about the intermediate representation that we came up with for hardware description. So this is an example of a load operation in HIR, our intermediate representation. First, you would see that we have all the normal components that load operation has, such as the memref on which the load is to happen, the index, and the data type. In addition, for hardware, we also have this port information. Hardware memories are multi-ported, and you have to specify in an FPGA which port you want to use to perform a load or store operation. So that is something we explicitly capture. You also have to specify the time at which the load operation should be initiated. And that's why we have a time variable. We will discuss about that later. And we also have a delay of 1 cycle in this specific example, which basically means that the load operation will take 1 cycle from when it starts to get back the data from the memory. Now let's take another example, which is a function declaration and a function call. So here you could see that in addition to the data type, we also capture the scheduling contract of the function. This is an external function that we support these function declarations so that you can plug in Verilog modules. And what happens is that the declaration captures the contract that the Verilog module requires in terms of scheduling with the user of the module. So here you could see that the Verilog module expects that the last input should come after a delay of 2 clock cycles from whenever the fused multiply operation starts. And the output will be available only after 4 clock cycles. And our compiler then statically checks that this is indeed the case. Okay, so here is an overview of the compiler. The pink blocks are something that we have taken from the MLIR infrastructure, and the blue ones are what we have implemented on our own. We could break the compiler roughly into 3 phases: the front end, the optimizer, and the back end. For the front end, we are using Polygust to lower C++ into the affine dialect, and we extended Polygust to support HLS-specific pragmas. For the optimizations passes basically take HIR and then perform certain optimizations that are relevant for our case. And finally, the backend lowers HIR into system Verilog. Okay, so first of all, let's discuss about the first pass, the first thing, that converting affine dialect into HIR. So this process is scheduling, and we have implemented an ILP-based scheduler that takes a sequential affine program and creates the parallel HIR schedule. So what do you mean by a schedule? So in this example, you can see that you have a load operation, an add operation, and a store operation. So what happens is, here HIR specifies that the load operation has to be triggered at some time Tj. Here, the actual absolute time doesn't matter. So we specify it using a time variable Tj, but the relation between the times do matter. So at time Tj, the load operation is initiated. And since the load has a delay of 1 clock cycle, its output is available at Tj plus 1. That's when the adder kicks in. And since it's a combinational adder, the output of the adder is also immediately available at Tj plus 1. And then the store operation can start at Tj plus 1. That's why it is the store is scheduled at Tj plus 1. And finally, the value is stored in the array CO at time Tj plus 2, as you can see in the timing diagram. Okay, so now we will discuss one of the optimizations that we implemented. This is called delay optimization. So the motivation behind this is that we saw that after our scheduling pass was done, if you have producer-consumer kind of loopness, the consumer loop requires a huge delay so that the producer loop has finished its operations. So we see delays which can range up to 30, 40,000 cycles. So here, what we observed is that usually these delays are in blocks which have very high initiation intervals. So what we do is we associated, we create a shift register and associate it with a state machine. So here you can see that originally you would, in order to have, let's say, a delay of 5, you would require 5 shift registers. And let's say you have an initiation interval of 2. In the optimized case, you only need 3 shift registers and a state machine. So if now every clock cycle, let's say in the first clock cycle, the value V1 is read by the desktop. In the optimized case, the desktop also reads the value V1, but it's just that we disable the shift register. The state machine disables the shift register's write enable, so that the shift register's value do not change on the right side in the optimized case. But on the left side, the values keep falling. In the next clock cycle, once V2 has reached the end, the destination op is about to consume V2. At this time, in the optimized case, we also enable the shift register so that V1 has dropped and V2 is now at the top. So in the next clock cycle, again, the same thing happens. We consume V2. But in the optimized implementation, the state machine again turns off the shift register so that the values are retained. So in a way, you could think that what this optimization is saying is that if you have an initiation interval higher than 1, then you have these unused registers in the unoptimized case, these bubbles. And that's what we optimize for by using the state machines. Okay, so next is schedule verification. We have these explicit schedules in the form of time variables. So we decided to use it to verify the program. So what we do is, let's take this simple example. You can, what our schedule verifier calculates is that op1 is at time t1, t plus 1, so that the next, the output of it is at time t plus 3 because the first call has a delay of 2. Similarly, for op2, since the delay is 3, the output of op2 is available at t plus 4. And now when it comes to the adder, the adder needs both its inputs at the same clock cycle, but the compiler can see that they're coming at different clock cycles. And this is how the schedule verifier can find pipeline imbalances. Okay, so now one of the passes in backend that I would like to discuss is inferring FSMs. So here is an example where we have a for loop, and what we are doing is we are taking the for loop and we are looking at the initiation interval for the for loop, which is 2 in this case, and we add a new FSM loop body. So here you could see that originally we had an FSM for the inside the body of the loop, and then we added another FSM for pipelining the loop. So this is how our compiler generates the finite state machine for the design recursively in a bottom-up fashion. Okay. Finally, we compared our work with Vitess HLS, and we saw that we actually outperform it by around 25 to 35% while consuming fewer lookup tables and flip-flops. The improved resource usage is because HIR statically schedules circuits, so we save on dynamic handshakings. And the performance improvement comes from our ILP scheduler, which can do better pipelining across loop nests. Thank you. Yeah, also, our work is open source, so please feel free to check it out. Thank you.
Hey, thanks for the great talk. This is Rachit from Cornell. In the last slide about the results, Vitess HLS also does static scheduling. So I'm not sure I quite followed.
Yeah.
Why.
So if you see the optimization, okay, to be specific, these performance improvements are coming from the data flow optimization. So these benchmarks have producer-consumer kind of loop nests. And the problem the limitation that Vitess HLS has is if you have, let's say, a producer loop and a consumer loop, then you have certain constraints in Vitess HLS. For example, if the producer is writing to an array and the consumer is reading from the array, the reads and the writes have to be in the same order. That is because internally Vitess HLS uses a FIFO to implement it. But since we are using an ILP-based scheduler, we don't have any such constraints. So, and in this specific cases where you have convolutions, the reads and writes are not only unordered, even the number of reads and writes are not the same. Because when you are doing the writes, you do one write for each value in the 2D in the image. But when you're doing read, you have a window of convolution. So you're reading the same value again and again. So that is why Vitess HLS was having a hard time optimizing this data flow.
Can you give a quick intuition of what the ILP solver is helping you reason about that Vitess cannot?
So what the ILP solver does is it can find out memory dependencies, right?
Got it.
Based on those memory dependencies, it can calculate what is the minimum slack required for the consumer loop to start so that it never runs into a data hazard.
Got it. So if you add that memory dependency to Vitess, it should be able to.
Correct.
Awesome. Thank you.
Thank you.
Hi, this is Julian from CodePlay. Very cool work. I wanted to ask about what is happening after you schedule with the ILP-based scheduler, and then later you do verification. So are you doing transformations with the scheduled data?
Yes. So if you see the, just one second, let me, where did it go? Yeah. So yeah, after the ILP solver, we have these optimizations that we perform. The delay optimization is one of the optimizations. We also do bit width reduction. And there is another delay coalescing optimization to reduce before we do the verification. So yeah, there are a few passes between the ILP solver and the schedule verifier.
And this would be inconvenient to integrate into the scheduler directly.
Yeah, first of all, that would make the scheduler harder. So it's general, it's a good idea in compiler to always try to break it into simpler passes. And also the scheduler and these optimizations are doing two different things. The scheduler is trying to maximize parallelism, whereas the optimizations afterwards are trying to reduce the resource consumption after the schedule has been decided.
Good, thanks.
Welcome.
Sorry, I had one more question.
Sure.
Can you talk about how the interfaces for partially pipeline modules work, if at all? And do you reason about potential structural hazards that come from pipelining? Or is that something the scheduler figures out and then make
Yeah.
sure the II is long enough that you don't run into
Yeah,
these.
can you tell me what you mean by partially
So
pipelined?
II greater than 1 in
Huh.
module,
So-
specifically external modules that have II greater than 1 being integrated into the scheduler.
Correct. So the way we work, okay. So for external modules, currently we do not support II greater than 1, but that is some thing that we intend to add later. That's just one more constraint for us. But for internal modules that we have, like basically things that are written in HIR, it does support II greater than 1. So the way we work is that you give the ILP solver a target initiation interval, and then the ILP solver will try to find a feasible solution. And then we have basically a design space exploration step, which basically does a binary search on the initiation intervals to find the optimal initiation interval.
Awesome. Thank you.
Welcome. Okay. Thank you.
Thank you, everyone, for coming to this session. And thank you to all of our speakers for staying on time. That is us finished here. We can have one last round of applause to our speakers. Thank you.